Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. Good morning, everyone. I think we'll go ahead and get started. It's a pleasure to welcome Alex Zalé to the podium. Alex is the alumni centennial professor of astronomy at Johns Hopkins University, and one of his many accomplishments is the architect for the Sloan Digital Sky Survey. I think he'll end up spending a little bit of time on that this morning, and I'd like to welcome Alex to the stage. Thank you.
Yeah, thank you. So I would like to talk today about how this data is leading to new discoveries in science. And I felt that so since we have been working with Microsoft a little over 15 years, and the first bits of the Sloan data have been put out 10 years ago, seemed like a really good time to go back and look back at what was the journey like and where is it leading. Oops. So it really all started with Jim. So he and I met in the mid-90s, and on the first day when we talked in BARC in San Francisco, he asked me, okay, tell me your 20 queries. So that was really Jim. He immediately cut through. And in this process, as we were working on the Sloan survey, he came to realize, and as we worked together, that science is about to change very dramatically. And data is changing the way we do science. It hasn't just changed the society as we know it. And in this process, there is so much data, the traditional ways of analyzing the data is not going to work. And also, it was very clear from his early papers that he saw the revolution coming. He postulated that the future of data-intensive computing will be in scale-out solutions. He advocated the use of cyber bricks. So where basically the disk drives will have such powerful controllers that the controllers can do all the computations. When you look around the architectures of Google and Facebook, it's not all that different today. So it is clear that we are not building scale-up supercomputers for the data processing, but the companies who are involved in data processing and data and large-scale querying like Bing have hundreds of thousands of computers, which are all basically filled up with disk drives. How do you effectively communicate with scientists? Instead of writing a 100-page requirements document, Jim advocated that we start with the 20 queries, which he immediately asked me. And I said, okay, this is easy. Then I wrote down the first 5 questions I could ask from the data. Then I started scratching my head. And then I could write down the next 5, probably in the next hour, and then I said, okay, let me take the rest and I will email you. And typically when you ask scientists the first knee-jerk reaction, what are the 20 questions you want to ask from the data? They would say that this is ridiculous. I'm a scientist. I want to ask anything and everything. But when you think about it, and as the scientists think about it a little bit, they realize that there is a prioritized order. There are some questions which are much more important. And we understand now that we have to answer those questions that every astronomer or every genomicist in the world wants to ask 100 times a day. Those have to run very fast. And we still have to do, of course, everything else. Anyways, so a lot of these conversations and interactions with Jim have been, I think, wonderfully captured in this book where so many people in this room contributed to this book, The Force Paradigm, which I think Dan also showed yesterday. So you can download this book, and I strongly recommend it for everyone. So my personal involvement with big data, or data altogether, started in 1992 when Johns Hopkins joined the Sloan Digital Sky Survey. And the technology was just right that astronomers up to that point where simply dealing with individual images. So a typical astronomer took a few images per night at the telescope, took the tapes home, and analyzed it at home in their workstation. But the technology was just becoming right that we could build some very large cameras, and also the computers were starting to get powerful enough that we could process the data. So we set out to do this very ambitious project. It started at the same time as the Human Genome Project, and sometimes we call it also the Cosmic Genome Project, to map the whole northern sky, build a special telescope with a huge camera, and do first an imaging survey of the sky in 5 colors, and then pick the most interesting objects, about 1 million objects, and take spectra to create a 3-dimensional map of the universe. And we were very ambitious, so we said, okay, let's take 2.5 trillion pixels of images, take about 10 terabytes of raw data, and then we will build a database out of this, which will be 0.5 terabyte. And starting in 92, we said we will build the telescope and the instrument, everything in 3 years, and then we will take another 5 years, so by 2000 we will be done. And every institution who participated had to build a certain part of the system, and I was working on the statistical properties of the galaxy distribution, spatial clustering, and I said, okay, if the data is not properly organized, I won't be able to do the science. So I signed up to build a database. I knew nothing about databases. I started learning, and luckily I met Jim. In the meantime, it turned out that we were overly naive and optimistic, and so in the end, basically, the survey did not even begin until 2000. So everything took a little bit longer. And we finally finished in 2008. So it was 16 years down in the trenches that we were working on on collecting and analyzing the data. And when we had to wrap up everything, we had 120 terabytes of data to take care of. The database is now 35 terabytes. And we took a little bit more of the sky, but it is clear that we totally underestimated the task of the data system. We totally underestimated how many features we need to extract from the data. But we were lucky. By having everything taken twice as long, Moore's law and Criders' law came to the rescue. So Moore's law is, everybody knows Moore's law, so that the computers, basically, this performance doubles every 18 months. But Criders' law is that the disk prices are falling by a factor of 2. Short of floods in Bangkok, of course. So this is one of the first images of the Sloan Digital Sky Survey. You can see that we were able to generate this. We have trillions of pixels of this. And we have roughly 500 million objects on the sky that we identified. And this is just a quarter of the northern sky. This is the clicker is a little bouncy. So this is a 3-dimensional map of the galaxy distribution, and you can see that it has these very structured bubbles. So there is a sort of like a random foam, but you see certain bubbles of a certain size, especially here. It turns out that those are the resonance frequencies of the universe when the universe was about 300,000 years old. So the universe was filled with sound waves, and this was one of the more unexpected discoveries, because when we started the survey, nobody thought that we will ever see this signal. And it's a phenomenal discovery. This enabled us to actually measure the curvature of the universe. We built with the Sky Server. So Jim and I really, most of the code was written, at least in the first few years, by the two of us. And then eventually more and more people joined in, and it became like a folk song. So everyone added a new verse or a new refrain to the whole thing. But we built also a front end on top of the database, which was aimed at smart high school students. And we tried to go away from the usual paradigm that you just present the forms, and then you have to basically type in some things into the forms, and then you push a button, and out comes some data. We tried to make it visually interactive and attractive. So in 10 years, looking back now, we just exceeded 1 billion web hits on the website. And, and this is astronomy, so a very narrow segment of science. In the world, there are 15,000 professional astronomers, just about. We are at 4 million distinct IP addresses of people who use the site. So it is obviously attracting people way, way beyond the professional astronomy community. And what we also see is the emergence of a new kind of scientist. It is not quite citizen science, because I would rather call it the internet scientists, the people who are very electronically savvy, and they would not necessarily, so they are not the same people who, for example, would go into the backyard to collect or do the bird watching. These are people who are, for example, want to contribute something to science, but they are very computer savvy and very familiar with internet apps. It turns out also that the professional astronomers are using a lot, and it became the world's most used astronomy facility today. So this is, in 2004, we were already ranked #1, and in 2009, we are still the #1 used astronomy facility in the world. And imagine this is a telescope where you really access it through the internet. It's a virtual telescope that is up day and night. And based upon citations, so this has bigger impact than all the $100 million telescopes or multi-$100 million observatories. So it also means that the astronomers were very quick to take on this new way of working. So basically, in preparation for this talk, I sat down and started to list all the spin-offs, so they didn't stop with the Sky Server. So we created, I will show in a minute, another interesting collaborative framework around the Sky Server called CastJobs.MyDB, written by one of my students. But then other disciplines started to take, not just in astronomy, so there are various astronomy projects. Galaxy Zoo, SuperCosmos, and UKITS is in Edinburgh. The Hubble is the legacy archive of the Hubble Space Telescope. These are all, we created a virtual observatory, and the Sky Query was one of the first web services. It was released, I think, a few weeks after Microsoft released the web services framework. Then Palomar, this is the famous Palomar telescope. It's doing a survey. It is using the Sloan server. It's using basically our software framework. Then here we built a database for radiation oncology, which was derived from the Sky Server. We built another database for environmental sensors and wireless sensor networks. We are now getting into genomics, and we are also getting into high-performance computer simulations. And of course, when you think about it, this whole genealogy would not be right without the Terra server. So Terra server was the origin of Microsoft Virtual Earth and actually Google Maps, everything. It was way, way before everybody thought of putting images online. And when Jim first built the Terra server, I think the first reaction he got was that why would anyone want to look in their backyard? It sounds like a joke today. Anyway, so I would like to go in the rest of the talk a little bit, cover all this, so to see all the impacts and how all the spin-off basically enable discovery in science, not just in astronomy, but much wider. So Galaxy Zoo was one of the first citizen science projects. It started in the UK by Chris Lintott, who was a postdoc in Oxford at the time. And there's a British TV program, The Sky at Night, which sometimes also features Brian May, the guitarist of Queen, and he helped to promote the site. The idea is to take images from Sloan and ask the public to classify them, whether it's a spiral or an elliptical galaxy, whether it's winding clockwise or counterclockwise. It was amazing. So in 2 days, we had more than 100,000 people signed up. And in a matter of a few weeks, we got about 40 million visual galaxy classifications. And we went live in middle of July. And by November, there was a major discovery made by a Dutch school teacher. This object called Hannes Voorwerp, the little green thing, you can see this little ring there. The telescope software, the Sloan software classified this whole feature as a reflection. So basically an artifact from the telescope. It turned out it was anything but. It is one of the most unique objects on the sky where all the energy comes out in a single emission line. And there is only one such object known in the universe. And this was discovered by a middle school science teacher. And the object has since been observed by the Hubble Space Telescope, by several other NASA satellites, and the VLA, the big array that was in the movie Contact. So after we built Sloan, it was obvious that this is going to be much more broad across astronomy, and there was immediately demand to connect the Sloan data to the rest of the astronomical data sets, and that led to the idea of the virtual observatory. And we created an NSF-funded project called the National Virtual Observatory. Then that led to an international organization, which is entirely grassroots. Nobody is funding it. It's called IVOA, International Virtual Observatory Alliance. And now we have a permanent facility in the US called Virtual Astronomical Observatory, which is on par with the National Optical Observatories or the National Radio Astronomical Observatory, NRAO and NOAO. And it created all sorts of web services which do, for example, things like taking footprints of this on the sky. So we know where every one of these different surveys or observations are pointing on the sky. And it turns out it turned into a very interesting spatial problem. We had to do sort of all sorts of things that we do in GIS on the Earth, but at a much higher precision. So imagine that we have to locate things on the Earth with a 5-centimeter resolution, at the same time have some objects which are basically covering half of the Earth. So that is the problem here. And we do need to do this basically constantly on demand. And this whole framework is now not just only used by Sloan, but the whole Hubble Space Telescope software framework has been converted. They converted to SQL Server. So several NASA satellites, Galax and Chandra, at Harvard, they have converted to SQL Server. Some new surveys, PennSTARS, is using this system. And while LSST is using a C++-based framework, they actually use now the library derived from our C# code. So LSST is also planning to use this whole thing. And this is the library that we have written. We wrote the first version of this with Jim in T-SQL. So imagine writing computational geometry in T-SQL. So you need Jim Gray on the team for that. But now it's actually a very compact package written in C# by Tamás Budavári. And we did a really nice automatic conversion. So our primary code base is in C#, but we can derive C++. We can also have a mono version of it that runs in Linux. So basically it runs on any and all platforms. Anyway, OncoSpace. So a friend of mine who is both a physicist and a medical doctor, Todd McNutt, heard about the Sky Server and came to us. This was around 2006. And they realized that they face very much the same problems in radiation oncology as we faced on Sky Server. They need active databases. They have too much data. So basically, all the CAT scans of the patients before and after the treatment and after every treatment, they want to see the progression of the tumors, and they want to see a time series whether the treatment works or not. And they want to use all this data to create immediate feedbacks to modify the treatment if it's not working and so on. So basically, they copied the framework and then modified the schema, of course, to be used with radiation oncology. And it has been now in use at Hopkins for over 5 years. Oops. So another life sciences project is Life Under Your Feet, where we built small wireless sensors and then try to monitor soil moisture, soil temperature, carbon dioxide input and output, or carbon dioxide output of the soil inside the soil and above. And it turns out that the soil is the largest unknown in the whole carbon cycle. And I heard Al Gore talking about this at one of the supercomputing meetings, and he said, if you take out a piece of Earth, it's black because of the carbon in it. And so we built a wireless sensor network. The whole database is, again, running SQL Server, same framework. except that we put in time series manipulations and so on. And this was one of the first applications of data cubes. So Stuart Ozer helped us to write the first paper on data cubes in science with this. Oops. Oops. This is glitching. So this is the number of data points or sensor data points that we have been collecting as a function of time. So we started seriously deploying just on the Hopkins campus in 2005. And by today, look at the scale. So we have 160 million data points measured from these sensors. And the deployments have been not just in the Baltimore, Washington area near Hopkins or at the Chesapeake Bay, but we had, so Dan showed yesterday some of the pictures from the Brazilian deployment. We had some measurements in the rainforest in Ecuador at Coca or near Coca. And also we had a 6 months deployment at the Atacama Desert in Chile. So here are some of the pictures. So this is one of the big deployments that we have. Each of these little signs is basically a sensor placed near a carbon dioxide flux tower. These are pictures from the Brazil deployment where it was measuring the atmospheric disturbances in the rainforest. And so there were some high towers and the sensors were hanging off these wires. So this is a picture from Atacama. Princeton has a big telescope, a sub-millimeter telescope there, and they have a nice internet connection, so we placed the sensors close to that site. And this shows a picture from the lab. You see probably some familiar faces. So, but what is emerging recently is a whole new ballgame. So it turns out these were all experimental data sets coming from where the data is coming from lab instruments. But what is also emerging today is that we have a lot of data coming from high-performance computing simulations, supercomputers, in other words. And e-science and supercomputing has been for a long time two distinct communities having different agendas. But what we see today, there's a convergence coming. So high-performance computing is becoming an instrument in its own right, and the largest simulations are reaching petabytes today. But what good does it do if we can't use them and we cannot touch them? So it brings up new sets of challenges, because people want to access these simulations and compare to their observations and experiments. So the challenges are, first of all, how do we move the data from the supercomputer to a place where we can use it? What is the right interface? What is the right paradigm to play with the data? How do we visualize it, and how do we analyze it? All sorts of scalability and metaphor issues. So this is when we moved 150 terabytes from Oak Ridge. It seems like, an easy thing in hindsight. Well, it wasn't. So we had a 10 gig network, but there were firewalls all along the way which were blocking the transfer. So in the end, we needed the head of Oak Ridge's cybersecurity talk to the guy who is running Starlight, which is the networking hub of the country, and the two had to make arrangements to actually punch holes in the respective firewalls. But hopefully this will get easier every time. How do we interact with the data? And I'd like to show, so we came up with a very interesting metaphor. So basically today, when people interact with big simulations, they download the files. And that works if the files are, few tens of gigabytes. When it starts to be tens of terabytes, it's very difficult to move the data. So our idea was to take basically a 30 terabyte simulation, which is 1,000 cube and an additional 1,000 time steps. This is about 30 terabytes. And build a SQL Server database out of this with a high spatial granularity, and treat it as a numerical laboratory. So turbulence is basically tornadoes in a box. And so the idea was then, if it's tornadoes in a box, why don't we play Twister in a box? You saw the movie Twister, where the guys drove up to the tornadoes and were shooting accelerometers into the tornado, which were then reporting back what this circulation is doing. This is what we do. You take your laptop, shoot 1,000 particles into the simulation, and they report back the fluid velocity. Those are the sensors. And the user who has the laptop doesn't know whether it's 30 terabytes or 30 petabytes, as long as the points come back with the report. So, and this works like a charm. We are now moving more and more simulations in this. This is a typical day of traffic on the site. So 100 million points on a good day. And we exceeded, but in 2011, we exceeded 100 billion points delivered to the turbulence community. And this is what we use. So we basically build a library similar to the spatial indexing that we built on the sky, except this is in 3D space. So we basically built an indexing system, a library built on space-filling curves, which means that points which are close to one another in 3D space are close to one another on the curve. And this means also they are close to one another on the disk. So as we are reading a chunk of data, we have a sequential read pattern, which goes much, much faster. And this maps beautifully onto the B3 index of a database. So this works very, very nicely, and we have it's easy-to-use generic library to do this. And this is leading to papers in PhysRev letters. We have more than 20 papers published, or not just us, but people in the world who are using this system. Cosmology, so I'm an astronomer after all. Cosmology is heading the same way. So in 2000, there was a big simulation done in Germany called Millennium. Generated 30 terabytes of data. It was written into a tape library, and nobody could get to it. Until one of the guys in Garching took the Sloan database, the Sky server, and basically modified it so he took the 1 terabyte of the simulation which represented the galaxies only, not the dark matter, and basically built a sophisticated database and took the CAS-JOPS interface that we were using. And essentially, he has now more than 1,000 users in that system. And became the reference simulation. There are much bigger, much better simulations today, but everybody is using this because it's easy. However, today's simulations have now 1 trillion particles and are exceeding a petabyte of storage space. So what do we do? And basically, the Millennium XXL is one of these, and they could only output 4 snapshots because they didn't have the disk space. So we are coming up, so unless this problem is solved, we are stuck. And this is a project that we just got funding from the National Science Foundation to take a petabyte scale simulation. But I showed the first 150 terabytes of this already were finished at Oak Ridge. And Jose is part of the team. We are trying to build it again into a SQL Server database and create an interactive environment. How people, and this would demonstrate clearly that you can today play interactively with a petabyte of data, and you can move it, you can visualize it. How do we visualize a petabyte? Okay, so with the analysis, we ended up sending the analysis to the data. We are now at a point when we have to send the rendering to the data, because we cannot send the data to where the rendering engine is. And it turns out that the bandwidth is, so typical bandwidth distribution is such that pretty soon every person in major countries will have access to essentially a high enough bandwidth to look at a 3D video stream in high definition, even on a mobile device. So this means that if we have this kind of proliferating, we can actually send these visual results of the visualizations anywhere in the planet. But the visualizations are becoming I/O limited. If you have a petabyte, you will still have to get that data into the GPUs. And so we started to play with prototyping. How can we do this? How can we integrate the visualization with the database that we don't have to even send the data across the network, but we can send it on the backplane of the database servers directly into the rendering engine? This is one of the pictures that was generated from the turbulence database. And here, and the next picture shows actually a movie where we were streaming the data. And let me try, oops. Does this start? Okay. Can we start? Okay, thank you. So this is streaming 24 million particles from the database into the GPU engine, and this is essentially a capture of a real-time movie. And here the streaming was going at a little over 1 gigabyte a second, limited by the bandwidth of that particular system. We can do now about 5 times better. So we can max out essentially the PCI bus. with. So so the hardware is our limit, not the software. So this shows just 3 layers, starting out with 3 layers and how the particles are basically moving in this turbulent flow. Okay. Next slide is the hardware. So in 2000, when we were getting ready to put the Sloan database out, Intel donated us a bunch of servers. We had a terabyte, which filled up a lab. We were building it out of little disks. In 2008, we built the revolves, which was funded by Microsoft and the Moore Foundation, and that was a petabyte at Hopkins. So this was all a big SQL Server cluster, and today we actually reached 8 petabytes in the same lab. And again, still running a distributed SQL Server on it. And this is the distribution of projects that people want to run on this new system that we call the data scope. It's with a hyphen, so it's different from the Microsoft. I don't know whether it's a trademark or not. But so basically, you can see that astrophysics is maybe the largest, but it's very uniformly distributed between high-energy material science, fluid dynamics, bioinformatics, environmental projects, ocean circulation models, atmospheric simulations, and so on. And the distribution of the data set sizes where people are kind of stuck and they need help is currently at around 100 terabytes. So if you have 100 terabyte-ish data sets, then we are happy to help. But besides the big data sets that I talk about, there is also an issue with the long tail. Long tail, on the web, everything has a long tail. And this means that we have a huge number of small data sets, but the integral of these little data sets is quite large because there are so many of them. And it also brings in a complexity issue that these data sets are also very complex. There is something to be learned here from Facebook. So what is Facebook and YouTube? In a sense, it starts out, take a whole bunch of many seemingly unrelated and irrelevant data bits together, and suddenly, if there is enough of them, suddenly new connections appear. And what you learn from a little subset, so somebody actually tags a picture with somebody's photo, then you can process all the other pictures on Facebook and then use the same tag. You can recognize the same face in other photos. So there is sort of a magical transition happens when you bring a lot of these small data sets together. So that's one lesson. The other lesson is Dropbox. Dropbox has this ultra simple interface that does very little, really. But it does it very well. And there is also a strength in having a totally crisp, minimalist interface that just does exactly what is needed and nothing else. And there is a lesson for scientists that basically simple interfaces are much more powerful than complex ones because nobody will take the effort to learn a complex interface. So how can we use this? And so we are starting to outline a project that we call Dropbox for Science. So we combine Dropbox and this MyDB, the server-side databases for all the scientists. So, and the notion of something called VO space, which is a storage for astronomy data. And the idea is that, first of all, we provide a carrot. So we provide something that is easy and attractive for everyone. So we provide for the first starting with the astronomy community because it's not too large. So let's provide a free cloud storage for the astronomy community. You can take your little images that you would otherwise store on your workstation and eventually would get lost and just drag it into this cloud storage. Okay, but that's not all. So then we start, as soon as you upload the data, you drag it into the Dropbox, we start harvesting the headers of the files and figure out the metadata. For example, where is this image on the sky? And we have a prototype where within 10 seconds that you drag an image into your folder on the cloud storage, you can already see in the context of the Sloan survey and the Hubble Space Telescope observations where your particular image is located. And you can also see that who else in the world has images on the same part of the sky. Then the metadata and the tables also go into MyDB, into a little SQL Server database. So if you have a tabular data like a CSV file and you drag it in again, then that table shows up in your space, and you can start joining this with all the other tables that your friends have, and your collaborators have. And this is not unlike Bill Howe built something called, I think, SQL Safe, But we also do the same thing with the metadata. So you can have a big collection of images, and then I can run a spatial query, get me all the objects from the Sloan survey that are within the footprints of all the images that I have. Okay. And then all the data can be immediately connected to all the other web services that are available for astronomy. And we think that this can be easily generalized to other areas of science. And we will, as a first challenge, we are going to take on environmental science, because around the sensor deployment, there is also 20 years of historical data, both from the fauna and the flora of this whole site near Baltimore. But the data is essentially unusable in the sense that almost every file is in a different format. So it is so hard manually to bring it all together. But if there was an automatic parser which all mapped onto a database schema, then this would make it much, much easier for the people to do it. And this is the rough layout. So you can get data in through drag and drop, and you can have some folders which sync with your laptop, others just stay server side. We have access to this through the VO space protocol, which connects to the rest of the VO services. I don't have on the figure, but we will also have the S3 API supported. So basically everything that talks the Amazon S3 protocol can also upload data here. We can have a distributed blob store, which can be at multiple locations. If one site goes down, then the data is still up. And then this all connects to the SQL Server database on the back end, where both the tabular data go and all the tables of the metadata. So we can run very efficient SQL searches on it. And at the very end, I would like to talk about all the important changes that this whole brings in the sociology of science, how we make discoveries. So what we see, first of all, that we see a convergence of physical and life sciences, because the same technologies are now deployed not just in physical sciences, but in life sciences from oncology, in genomics. People are running computer simulations in systems biology, trying to put the metabolic pathways into databases. So it's starting to converge through computing. Data collection is happening in ever larger collaborations. Just look at all the virtual observatories on every level of the physical scale. So from CERN for the high energy physics, VAO for astronomy, NCBI for genomics, NEON for the environment, OOI for the oceans. And all this data is put into public archives, and the analysis is decoupled. A whole different community goes and analyzes this data, who are different from the people who collected the data. And if somebody, a single individual, has a clever idea, he or she can go now to these databases and do wonderful science. We see the emergence of the citizen/internet scientist. And also there are some important demographic changes coming. The baby boomers are about to retire. And a lot of people, retirees, for example, go on archaeological expeditions, and they pay their own way. But there are all these highly sophisticated computer-savvy people who are retiring, and they're looking for something exciting to do. And there is all this data out there. So there is an enormous intellectual capital there to be harvested and used, and channeled in the right direction here. So I think it gives us a wonderful opportunity to have people who tutor young kids who are also eager to find new discoveries. And we need to start training the next generations. And traditional scientists are eye-shaped. They are very narrow and deep in their own field. And this is what our whole higher education system is geared towards. But in this world, when we have these large amounts of data, we need people who not only understand what the data means, but they also understand how to put it, how to format it, how to analyze it, how to manage it, how to design algorithms that can perform the analysis fast. So we need people who are pie-shaped, who are equally at home in their own disciplines and computer science. And the trouble is that in science, in a scientific career, people don't have the time later on. This has to be started early. Preferably even in grad school. The latest I can imagine this happening is in grad school. And so we need an early involvement in computational thinking. So summarizing, science is increasingly driven by data, both large and small. And we have these large data sets here, but we don't have the cheap off-the-shelf solutions. We still don't have it here. We see a changing sociology of science, so this is changing science as we know it. And science is moving from hypothesis-driven to data-driven science. And I would like to reflect on this, that it is very rare in the history of mankind that we live through a scientific revolution, but it's happening now and today. So please realize what a special time we live in today. We also have the problem on the long tail, not just with the big data sets. We have the same problems in business and society. So we have to figure out if it's not enough to train these smart people who are data savvy, but we also have to provide them academic rewards that at least some of them stay in academia and don't get snapped up by Wall Street and by the defense industry. Data changes not only science, but society. And we see this new force paradigm of science emerging, and Jim is smiling. And I would like to thank everyone at Microsoft for this 15-year journey. So it was really an amazing journey. And I think I tried to give you a little look back on I think, what has happened over the last 15 years. Thank you very much.
Thank you, Alex. We started a little bit late, so I think we'll ask you to take on questions out in the lobby, and we'll move on to the next speakers. Thank you again, Alex. So I'd like to welcome the two leaders of the LACCIR Collaborative Research Federation, Ignacio Casas, the Executive Director, and Sergio Ochoa, the Deputy Director. So please join me in welcoming Ignacio and Sergio.
Thank you, Jim. Good morning, everybody. Buenos días a todos. This presentation is going to be in Spanglish, a little bit of Spanish, a little bit of English, and perhaps a little bit of Portuguese as well. Les vamos a contar hoy día sobre nuestro trabajo en el Instituto Virtual LACCIR. En los últimos 5 años, el Instituto Virtual LACCIR nació en el año 2007, en mayo de 2007, en respuesta a un llamado de Microsoft Research para crear una comunidad virtual de investigadores en el área de ICTs y Computer Science en Latinoamérica y el Caribe. Y estamos aquí en nuestro 5º año y queremos contarles y rendir cuentas de lo que hemos realizado y pensar un poco cómo vamos a seguir en las siguientes etapas hacia adelante. Vamos a mostrarles brevemente lo que es LACCIR, nuestra estructura, quiénes son nuestros stakeholders, los participantes, nuestras actividades principales, nuestros logros a la fecha en 5 años. Les vamos a mostrar la carpeta de proyectos que hemos estado realizando y financiando en estos 5 años. Les vamos a mostrar un poco del Research Observatory que hemos construido para darle visibilidad a los investigadores y a sus proyectos en la región. Y les vamos a contar del nuevo Request for Proposals que estamos anunciando hoy día en este evento con las bases para que se entreguen las propuestas, se elaboren las propuestas. Están las condiciones en este brochure, las pueden obtener también en el sitio web de LACCIR y los invitamos a que participen. Y tenemos más información, además de invitarlos al sitio web de LACCIR. En este librito que sacamos es una memoria de las actividades de LACCIR, donde están descritos los proyectos y nuestras actividades principales. Los distribuimos en el lobby aquí del hotel. Si se quedaron sin alguno de estos libros, por favor envíenme un correo electrónico y yo se los envío a sus direcciones para que tengan una copia en sus oficinas. Entonces vamos a partir contando sobre LACCIR, nuestra estructura. Pensamos que lo mejor era mostrarles a través de nuestro sitio web, del cual estamos muy orgullosos, que hemos construido con herramientas de Microsoft. Pues, por favor, visítenlo. Tenemos mucha información ahí que es relevante para todos los investigadores de la región. Esto lo hemos construido utilizando herramientas de Microsoft como Silverlight, DeepZoom, Pivot, SQL Server y otras herramientas. Y estamos muy orgullosos de este sitio web. Tenemos también comunidades virtuales en Facebook, en Twitter, LinkedIn, YouTube, y los invito a que participen en ellas. Bueno, primero sobre quiénes somos en LACCIR y cuáles son nuestros objetivos. Tenemos aquí en este slide, en esta página del sitio web. Me faltó el mouse aquí. Bueno, como les decía, LACCIR fue creado en 2007 en respuesta a un llamado de Microsoft Research para crear esta comunidad de investigadores en la región, para darle visibilidad, para hacer redes de contactos y para superar un efecto de falta de masa crítica que tenemos en la región. Nuestros grupos de investigación son muy pequeños, somos grupos de 10, 15 investigadores en cada una de nuestras universidades dedicados a Computer Science y tenemos poca colaboración entre nuestros países. No es fácil que un argentino trabaje con un chileno, pero lo hemos logrado ahora. Y estamos muy orgullosos de que efectivamente hemos logrado estas redes de colaboración y pensamos que estamos teniendo bastante más productividad ahora. Nuestro objetivo ha sido el de impulsar la investigación en ICTs y Computer Science con fines de lograr impacto en el desarrollo social y económico de nuestros países. Tenemos una organización con un grupo de universidades. Tenemos un hub administrativo en Chile, en la Universidad de Chile y la Universidad Católica de Chile, y tenemos un grupo de universidades que llamamos spokes, que están encargadas de difundir y acercar a todas las universidades de su propio país y del área de influencia para participar en estas redes de colaboración de investigadores. Tenemos al Tecnológico de Monterrey, al Politécnico Nacional aquí en México, la Universidad de Buenos Aires en Argentina, la Universidad de Costa Rica, la Escuela Superior Politécnica del Litoral en Ecuador, la Universidad de la República en Uruguay, la Universidad de los Andes en Colombia y la University of West Indies en el Caribe, basada en Trinidad y Tobago. Tenemos un grupo de stakeholders, siendo nuestro principal stakeholder Microsoft Research, quien generosamente nos ha provisto financiamiento para nuestros proyectos de investigación. Como les mencionaba antes, hemos tenido también financiamiento del Banco Interamericano de Desarrollo, tenemos financiamiento de CONACYT para trabajos de investigación en colaboración con universidades mexicanas, y para pasantías de estudiantes de posgrado aquí en universidades mexicanas. Tenemos el apoyo de la Organización de Estados Americanos, que nos da los contactos con los ministros de Ciencia y Tecnología de cada uno de nuestros países y nos da los lineamientos hacia dónde enfocar nuestros aportes de investigación. Y tenemos las universidades en el hub que aportan con la administración. Y como les decía, nuestros objetivos son principalmente crear oportunidades de investigación para los investigadores de nuestros países, de acá de Latinoamérica y el Caribe, en áreas de computer science, ICT, en distintas áreas de aplicación, buscando siempre un impacto a nivel social y económico de nuestros países. Y le damos oportunidades también a nuestros estudiantes para darles movilidad dentro de la región, para tener estudiantes de posgrado, de magíster y doctorado, intercambiando con estudiantes en distintos países. Bueno, eso es con respecto a nuestra estructura. Con respecto a nuestras actividades principales, tenemos las siguientes. Las principales actividades de LACCIR se refieren a los Requests for Proposals. Este año estamos lanzando ahora nuestro 6º Request for Proposals. Cada año, desde el año 2007, hemos hecho Request for Proposals, lo que nos ha llevado a financiar hasta el año pasado 28 proyectos de investigación. Normalmente recibimos para cada Request for Proposal recibimos entre 30 y 40 propuestas y seleccionamos 5, 6 o 7 propuestas para ser financiadas con los fondos de Microsoft Research y del Banco Interamericano de Desarrollo. Tenemos también un programa que le llamamos el Short Stays Program, donde entregamos pequeños financiamientos a estudiantes del orden de $5.000 para que hagan pasantías cortas de 3-4 meses en universidades de nuestra región. Hemos tenido del orden de 30 estudiantes que han estado participando en esta movilidad para estudiantes de posgrado. Tenemos también lo que llamamos las escuelas de verano, summer schools o doctoral academies. Ya realizamos la primera a principios de este año en Santiago de Chile y esperamos tener una segunda escuela de verano a principios del próximo año, probablemente en San José, en Costa Rica. Hemos postulado a la National Science Foundation para tener financiamiento, para tener esta escuela de verano en Costa Rica y donde esperamos tenerlos a todos ustedes y sus estudiantes participando acá. Colaboramos con Microsoft Research en sus programas de fellowships, internship, promoviéndolos en la región, invitando a nuestros estudiantes y profesores a participar, y también colaboramos con Microsoft Research en el Faculty Fellowship Program. Esas son nuestras actividades principales. Y en cuanto a los achievements, los logros, de los cuales nos sentimos bastante orgullosos, les podemos mostrar, pueden encontrar toda esta información en el sitio web de LACCIR, los logros más importantes. Bueno, con respecto a Request for Proposals, como les decía, hemos hecho todos los años estos llamados a concurso. Tenemos 28 proyectos que hemos estado financiando. Tenemos 126 investigadores de la región que están participando en estos proyectos. Hemos a la fecha logrado 123 publicaciones en revistas indexadas internacionales y esperamos del orden de 80 a 100 nuevas publicaciones este año. Tenemos el Short Stay Programs, tenemos 32 estudiantes que han utilizado este programa y se han movido en la región de un país a otro por estadías de 3 a 4 semanas, involucrando del orden de 13 países de la región. Tenemos una red de colaboración de investigadores del orden de 500 investigadores trabajando en proyectos y actividades fomentadas por LACCIR, con más de 80 instituciones de la región, universidades y centros de investigación, uniendo a 19 países de Latinoamérica y el Caribe. Tenemos el Research Observatory, del cual Sergio les va a contar un poco más, las escuelas de verano que ya les mencioné, y hemos tenido participaciones en conferencias internacionales, sobre todo las de la Organización de Estados Americanos, con los ministros de Ciencia y Tecnología, mostrando nuestras actividades de LACCIR. Tenemos los financiamientos que les había mencionado anteriormente. Hemos podido utilizar las plataformas de Microsoft para nuestros desarrollos y para facilitar la conectividad entre los investigadores y, como les mencionaba, la red de contactos que a través de las herramientas de Microsoft, por ejemplo, Live Meeting, hacemos videoconferencias, compartimos documentos, compartimos objetos y con eso facilitamos esa comunicación. Eso con respecto a los logros. Ahora Sergio les va a contar sobre los proyectos específicos de LACCIR.
Muchas gracias, Ignacio. Como mencionaba Ignacio recién, les voy a contar un pequeño overview del tipo de proyectos que se están realizando en LACCIR. Ustedes han tenido esta semana la oportunidad de ver algunos de ellos. Y la idea es que ustedes vean que los proyectos que se hacen en LACCIR tienen, de partida son interesantes y tienen un impacto importante en la región tratando de resolver problemas, muchos de ellos que son particulares de la región y otros no tanto, otros son más globales. Respecto de los proyectos, nosotros tenemos 6 áreas en las cuales estamos trabajando, hemos estado trabajando hasta el momento. La primera de ellas es Earth, Environment and Climate Change, otra área es e-government, educación, healthcare, microeconomies and energy. En la primera área tenemos un par de proyectos que fueron financiados por LACCIR y presentados ayer, por ejemplo, Live Andes, del profesor, liderado por el profesor Cristian Bonasic, también participan Luis Pacheco y Gerardo Ceballos. Es un proyecto que apunta a identificar poblaciones de especies en peligro de extinción y movimientos de ellas, muy relevante para toda la región. En particular se está haciendo una prueba de concepto en Chile. Otro de los proyectos que fue presentado ayer, ANURA, por el profesor Eduardo Nakamura. Participan Eduardo Vallejo, Antonio Laureiro y Alejandro Freri. Que básicamente lo que tratan de hacer en el proyecto es identificar y clasificar poblaciones de ranas y sapos en la selva de la Amazonía, tratando de, a través del reconocimiento del sonido, ver si existen nuevas especies en la región y también cómo ellas se mueven. Otra de las áreas en las cuales nosotros hemos estado trabajando es e-government. Solo voy a mencionar algunos de los proyectos por una cuestión de tiempo. Time Saver es un proyecto en el cual participa el profesor Flavio Soares y la profesora Rosa Alarcón, Brasil y Chile respectivamente. Es un proyecto que intenta reducir el tiempo que los ciudadanos normalmente gastan en hacer trámites en oficinas de gobierno, y para ellos proveen mundos virtuales que a través de esos mundos virtuales y la integración de servicios de gobierno permiten reducir considerablemente el tiempo que las personas gastan en ese tipo de trámites. Otro interesante proyecto es un proyecto llamado Mobile Map, que básicamente lo que busca es reducir el tiempo de respuesta en emergencias cotidianas, principalmente es aquellas en las cuales participa bomberos, donde normalmente reducir el tiempo de respuesta en 4, 5, 6 minutos, en caso de un incendio, por ejemplo, en el caso de un choque con consecuencias graves, es sumamente importante respecto de la cantidad de daño que produce esa emergencia. Bueno, este proyecto busca reducir tanto como se pueda el tiempo de acceso de los primeros recursos de asistencia al lugar de emergencia. En el área de educación también tenemos varios proyectos. Estos son los que están financiados. Ustedes pueden revisarlo después con calma. Hay un detalle de cada uno de ellos. Cliqueando aquí, ustedes van a poder encontrar un detalle de ellos. Este proyecto de educación, liderado por el profesor Miguel Nussbaum, busca, a través del uso de videojuegos, estimular el pensamiento crítico y la capacidad de resolución de problemas de los niños. Hay otro proyecto liderado por el profesor Luis Guerrero, participa también el profesor César Collazos, de Colombia. Básicamente lo que ellos buscan es tratar de reemplazar el cuaderno físico por un cuaderno digital y ver cuáles son las ventajas en términos de compartir apuntes, no solo entre estudiantes, sino también entre estudiantes y profesores, incluso durante la clase, o responder exámenes en línea. En el área de salud también tenemos varios proyectos financiados. Por ejemplo, hay un proyecto liderado por el profesor Eduardo Grampín de Uruguay, en el cual aborda la problemática asociada a la privacidad de las imágenes que circulan en las redes de los hospitales o de las clínicas, y que claramente es información sumamente sensible que tiene que ser protegida, por un lado, en forma apropiada, y por otro lado, permitir que aquellos que tienen que tener acceso liberado a ese recurso lo puedan hacer sin mayores contratiempos. Tenemos también, por ejemplo, el proyecto liderado por Alicia Díaz. Menciono solo algunos y estoy tratando de mencionar aquellos proyectos que he visto que los PIs están aquí, así que pueden conversar con ellos si quieren. El proyecto que lidera Alicia Díaz, Regina Motz, también participan Diego López Gutiérrez y José Valdeni. Básicamente lo que trata es de generar un ambiente en el cual se pueda obtener buenas recomendaciones respecto de tratamientos de salud. Y una cosa interesante es el enfoque que ellos usan, que básicamente es filtrado de información colaborativa, y la información de base es obtenida a través de desde redes sociales especializadas, y en base al procesamiento de esa información y el filtrado colaborativo ellos logran generar recomendaciones pertinentes para ciertos tratamientos médicos que la gente necesita. Respecto de microeconomía, también tenemos, algunos de estos proyectos han sido presentados en summits anteriores, ¿sí? Por ejemplo, el proyecto de Juan Nolasco y Kim Malaliu de la Universidad de West Indies, trata de enseñarle a la gente de menor recurso comportamiento financiero. Muchos de ellos, la hipótesis que maneja el proyecto es que muchos de ellos no tienen un buen comportamiento financiero debido a que no tienen la posibilidad de acceso a recursos bancarios. Entonces, este proyecto lo que busca es, a través del uso de dinero electrónico, generarle costumbres, ¿sí? Como por ejemplo el ahorro, que son sumamente sanas para comunidades que son sumamente pobres. Otro de los proyectos que también ha sido presentado aquí en este summit en versiones anteriores, liderado por el profesor Domingo Meri y Gustavo Gutiérrez González, es el análisis de la calidad de los productos en base a imágenes, análisis automático y en línea, y en base a eso la clasificación. Ellos trabajaron en un prototipo para la clasificación automática de la calidad de las tortillas en una fábrica de tortillas aquí en México, con muy buenos resultados, por cierto. Y la última área que tenemos, que es relativamente nueva, todavía no tenemos proyectos en esa área, pero está en nuestro interés tenerlos en el corto plazo, es básicamente proyectos asociados al área de energía. Tenemos también, mencionó brevemente Ignacio, el Observatorio de Investigadores Latinoamericanos, que está en este momento en estamos poblándolo, tenemos más de 1.700 investigadores en el área de Computer Science ya catalogados y disponibles en la base de datos. Aquí pueden ver los números. De Brasil tenemos 425, de Chile 404. O sea, en realidad consideren que la base de datos está estamos poblándola en este momento. Hay una buena cantidad de gente dentro, pero los números todavía no son representativos de lo que realmente hay en la región, ¿okay? Para que lo tengan en cuenta. Este observatorio tiene dos objetivos. El primero de ellos es que cualquier investigador de aquí o de afuera que quiera identificar gente que está trabajando en su misma área lo pueda hacer en forma relativamente fácil y rápida. Normalmente cuando uno quiere postular un proyecto o saber quién está por aquí en la región trabajando en los mismos temas, pretende acceder a algún sitio que le permita acceder a esa información en forma rápida. Bueno, este portal de observatorio de investigadores busca un poco ese objetivo. El otro objetivo que busca también es poder establecer una especie de métrica, ¿sí?, donde las organizaciones se puedan comparar, incluso los países se puedan comparar. En este momento solo se van a poder comparar en términos de cantidad de investigadores del área, ¿sí? Una iniciativa paralela en la cual estamos trabajando ahora, que es complementaria a esta, es en las publicaciones de estos investigadores que están acá adentro. O sea, probablemente en el próximo Summit les vamos a poder mostrar, digamos, la performance por institución, por académico, por país, en base a las publicaciones que estas personas tienen. Podemos filtrar información, por ejemplo, por país. Podemos ver México. Incluso, bueno, hay varios filtros que se pueden usar. No me voy a ir en detalle a verlos todos. Por ejemplo, podemos filtrar dentro de México por institución, ¿sí? Por ejemplo, no sé, CICESE. Ahí podemos ver los investigadores de CICESE. Podemos filtrar los investigadores de CICESE, por ejemplo, por área. Sistemas distribuidos, concurrentes, sistemas colaborativos. Una ventaja que tiene este portal es que algunos investigadores se ven más joven. Por ejemplo, el profesor Jesús Favela, que anda por aquí. No es que él se vea más joven, es un ejemplo nomás. Bueno, pueden ver las áreas en las cuales él trabaja, ¿sí? La información de contacto, y, como les decía, en la iniciativa complementaria que estamos trabajando, van a poder ver las publicaciones que él tiene, de manera tal de que ustedes puedan hacer una selección un poco más fina respecto de si él trabaja exactamente en el área que yo ando buscando o no. Lo pueden acceder al observatorio a través del portal, así que está disponible, y cualquier sugerencia, por favor, envíennosla. Estamos trabajando en eso. Y creemos que puede ser una muy buena herramienta para toda la región, fundamentalmente porque no es fácil encontrar o identificar quién trabaja en la misma área que nosotros en nuestros países. La última cosa que les quiero mencionar es, ya brevemente lo mencionó Ignacio, es la apertura del nuevo Request for Proposal de este año. La información completa está disponible en el sitio web, ¿sí? No me voy a extender en esto. El deadline es el 7 de septiembre. Se va a estar dando el veredicto. Están los brochures en las sillas de ustedes y ahí también fuera. El veredicto va a estar saliendo alrededor del 31 de diciembre, supongo que el 30, porque el 31 vamos a estar celebrando. Algunas cosas interesantes y algunos cambios respecto de los Request for Proposal pasado. Este nuevo llamado está enfocado a proyectos de investigación en áreas como Data Driven Discovery, Data Fusion, Visualization, Natural User Interfaces, Machine Learning, Semantic Computing and Network Systems, aplicados a Healthcare, Education, Environment and Climate Change, Social Computing and Microeconomies. un cambio interesante que tienen también el Request for Proposal de este año es que los proyectos, a diferencia de años anteriores, pueden ser por 2 años, pueden ser formulados por un periodo de 2 años, donde claramente hay un checkpoint al final del primer año y si el proyecto va bien, como normalmente ocurre, ese proyecto tendría financiamiento por 2 años con un máximo de $50,000 por año. Ignacio. Muchas gracias.
Gracias, Sergio. Thank you very much, Sergio. Al principio prometí que íbamos a hacer esto en inglés, castellano y portugués, así que ahora viene la parte de portugués. Pensamos que este Research Observatorio es o más grande do mundo, lo que hemos construido. Bueno, esa era la parte. Bueno, para cerrar, queremos nosotros con este Request for Proposals que estamos lanzando en este momento, pensamos que damos por terminado, cerrado una primer ciclo de LACCIR. Y estamos ahora en un brainstorming de cómo podemos seguir hacia un segundo ciclo, a second stage. We feel very proud of what we have accomplished. We can say, Dr. Tony Hay, we think that this is mission accomplished in terms of the objectives we defined 5 years ago, and we believe now that we have to go to a second stage. And we believe that we shouldn't continue with this open type of request for proposals, but we should move now to more specific research projects and using our network for the discovery of common links with Microsoft researchers, and try to use our infrastructure as a connection, as a link to find this common ground with Microsoft researchers and move now to more specific projects working together with Microsoft researchers. So, muchas gracias. Thank you very much. Muito obrigado.